A telescope 1 million miles from Earth just looked back to the edge of time, and what it found broke the rules. Fully formed galaxies existed just 300 million years after the Big Bang. Giant black holes appeared before they should have. Water vapor confirmed on a world over 100 light-years away. We will walk through 33 discoveries that James Webb forced science to reconsider, from the birth of the first stars to the possibility that the universe is older than we ever calculated. If you enjoy this journey, subscribe and stay with us. Every chapter goes deeper. Prepare yourselves. We begin. The discovery that broke cosmology's first rule. 1 million miles from Earth, a telescope pointed at nothing. A tiny, dark, unremarkable patch of sky. And in that nothing, it found everything. James Webb Space Telescope, launched on December 25th, 2021. Scientists had waited for it for decades, 30 years of planning. $10 billion. A mirror the size of a tennis court, folded like origami to fit inside a rocket. When it finally reached its destination and opened its golden eyes, the scientific community held its breath. They expected confirmation. They expected Webb to sharpen what we already knew, to fill in the gaps of a model that had taken generations to build. That model, the standard story of how the universe formed and evolved, had survived every test thrown at it for over half a century. Webb shattered it in the first few months. The telescope detected galaxies, fully formed, massive structured galaxies, spinning and blazing with starlight. That alone sounds unremarkable. Except these galaxies existed at a point in cosmic history when the universe was less than 500 million years old. And according to every model we had, galaxies that large, that organized, had no business being there. Picture building a skyscraper. You need to pour a foundation, let it cure, stack floors one by one, run wiring, add glass. The process takes years. You cannot skip steps. Gravity works the same way when building galaxies. Gas clouds collapse slowly. Stars form gradually. Gravity pulls them into clusters over hundreds of millions of years, then billions. The process has a minimum speed. You cannot rush it. Webb found skyscrapers that appeared before the concrete had time to dry. Astronomers confirmed the detections multiple times. They cross-checked the data. They ruled out instrument error. They checked the math. The galaxies were real. The distances were accurate. The timescale was correct. And the conclusion was unavoidable. Something in the early universe built structure far faster than physics said was possible. A team at the University of Edinburgh analyzed several of these early galaxies and found that their combined mass exceeded what the standard model predicted should exist across the entire observable universe at that age. Confirmed, peer-reviewed, repeated across independent research groups on 3 continents. This was not a rounding error. The gap between what existed and what should have existed, measured in factors of 10. Scientists started using a phrase that physicists almost never use in public. We might be wrong about the beginning. Here is what makes this discovery stranger than it first sounds. Every number in cosmology connects to every other number. The age of the universe, the rate of its expansion, the timeline of galaxy formation, the nature of dark matter. Pull one thread and the whole fabric shifts. Webb did not pull one thread. It grabbed a section of the fabric and tugged hard. If galaxies formed faster than our model allows, then either the model is incomplete, or the conditions right after the Big Bang were fundamentally different from what we assumed. Both options rewrite history. One of them rewrites it completely. And the galaxy discoveries were only the first signal, because hiding inside Webb's early data was something even harder to explain. A population of black holes, appearing at the center of these early galaxies, already enormous, already ancient, growing at a speed that our best physics says requires more time than the universe had given them. The telescope had barely started, and already the timeline of everything was bending. How Webb actually sees the universe? To understand what Webb found, you first need to understand how it sees. Your eyes detect visible light, a narrow slice of the full spectrum of radiation that fills the universe. Visible light bounces off objects, travels to your eyes, and your brain builds a picture. Simple, familiar, and deeply limited. Webb sees infrared light, heat, radiation. the kind of energy that every warm object in the universe constantly emits, including stars burning billions of light years away. This matters for one specific reason that changes everything about what the telescope can observe. Space is full of dust, enormous clouds of gas, and microscopic particles that block visible light completely. The regions where stars are born sit buried inside these clouds. The early universe, dense and hot and packed with swirling matter, was even more obscured. Optical telescopes like Hubble looked at those regions and saw walls, opaque curtains of dust with nothing readable behind them. Infrared light passes through dust the way a radio signal passes through a wall. Webb does not see a curtain. It sees through it, straight into the nurseries, the collapsed cores, the earliest moments of star formation, regions that were completely invisible to every instrument, before Webb now glow with detail. The mirror matters too. Webb's primary mirror spans over 21 feet across, made of 18 hexagonal gold-coated segments that work together as one surface. Gold reflects infrared light with exceptional efficiency. The mirror's size determines how much light it collects, and more light means seeing fainter, more distant objects. Hubble's mirror measured under 8 feet. Webb gathers roughly 6 times more light. Then there is the location. Webb orbits at a point called Lagrange Point 2, 1 million miles from Earth, in the direction away from our star. At that distance, Earth, the Moon, and our star all sit on the same side of the telescope. Webb's massive sunshield, a layered barrier the size of a tennis court, blocks all of their heat and light simultaneously. This keeps Webb's instruments cooled to around minus 448 degrees Fahrenheit. At that temperature, Webb's own heat cannot interfere with the faint infrared signals it is trying to detect. Here is the detail that reframes the entire mission. Infrared light from the most distant galaxies has been traveling for over 13 billion years. During that journey, the expansion of the universe stretched the light waves. What started as visible or ultraviolet light stretched into infrared by the time it reached us. An optical telescope would miss it entirely. Webb catches it perfectly. Its design was built around this physics deliberately. Think of it like tuning a radio to a specific frequency. Every other telescope was tuned to the wrong station to hear the universe's oldest signals. Webb is tuned precisely right. The first time Webb's instruments opened and locked onto deep space, engineers at the Space Telescope Science Institute watched the calibration images load. They were testing alignment. They were not yet doing science. And already, in the background of those test images, hundreds of galaxies appeared that no catalogue had ever recorded. Before the science formally started, Webb had already found things. That is the machine. Precise, cold, golden, and perfectly positioned to hear frequencies the universe has been broadcasting since near the beginning of time. And what those frequencies carried back to us was stranger than the engineers in that control room could have imagined. Galaxies that had no right to exist. The first confirmed images came in July 2002. The world watched. World leaders gave speeches. Scientists cried at their desks. But the image that quietly rearranged everything came in the weeks that followed. A series of spectrographic readings. Not dramatic color photographs, but data. Graphs showing the chemical fingerprints of light stretched across billions of light years. And inside that data, something that stopped researchers mid-sentence. Galaxies. Massive ones. Already fully assembled. Already glowing with the warm, settled light of mature stellar populations. Existing at a point when the universe was only about 3 to 4% of its current age. To understand why this is alarming, you need to know how galaxies are supposed to form. After the Big Bang, the universe was a nearly uniform fog of hydrogen and helium. Tiny variations in density caused gravity to slowly pull gas together. Over hundreds of millions of years, the first small clouds collapsed into the first small stars. Those stars formed clusters. Clusters merged across vast timescales into proto-galaxies. Proto-galaxies merged into galaxies. The process was glacial, methodical, governed by the speed at which gravity can move matter across cosmic distances. That process has a firm lower time limit built into the physics. You cannot compress it indefinitely. There is only so fast that matter can collapse and structures can merge before other forces push back. Webb found galaxies that compressed the entire sequence into a fraction of the time our models allowed. One of the most striking early detections carries a name scientists have shortened to the Maisie's Galaxy, discovered by a team at the University of Texas, who named it after a researcher's daughter on her birthday. Confirmed at an age placing it at roughly 390 million years after the Big Bang, its stellar mass was enormous. Its structure was coherent. It looked like a galaxy that had been quietly forming for billions of years, not hundreds of millions. That one galaxy alone forced a revision of timelines. Then came dozens more like it. A team analyzing Webb's first deep field data found at least 6 massive galaxy candidates existing before the universe reached its first billion years. Their combined mass challenged calculations that described the entire observable universe at that period. 6 galaxies, each individually carrying mass that the standard model predicted should require far more time to accumulate. This is where the science gets genuinely unsettling. The standard model of cosmology, the model that accurately predicted the cosmic microwave background, the expansion rate of the universe, and the large-scale structure of the cosmos, has no natural way to produce these galaxies this fast. Some scientists propose that star formation in the early universe was far more efficient than in the modern era, stars forming with almost none of the wasted energy and disruption that slow the process today. An early universe operating in a kind of high-efficiency mode that later switched off. Plausible, testable, still unconfirmed. Others suggested the initial fluctuations after the Big Bang were stronger in certain regions than standard inflation theory predicts, seeding larger clumps of matter that could collapse faster. Also plausible, also unconfirmed. Both explanations require additions to the standard model. Amendments, patches, and patches on a theory raise their own questions. The galaxies were real. The timescales were confirmed, and the explanation for how they existed remained, and still remains, genuinely open, which made the next signal from Webb's data even harder to absorb. When the standard model started to crack, for decades, cosmologists had a story they trusted, a precise, mathematically elegant story about how the universe grew from a hot, dense point into the vast, structured cosmos we inhabit today. The story is called the Lambda CDM model. Lambda refers to dark energy, the force driving the universe's accelerating expansion. CDM stands for cold dark matter, the invisible scaffolding around which visible matter clusters to form galaxies and large-scale structures. Together, these two ingredients, plus the known forces of physics, produced a model that matched observation after observation with remarkable accuracy. Predictions about the ratio of hydrogen to helium after the Big Bang, confirmed. Predictions about the faint temperature map of the early universe called the cosmic microwave background, confirmed. Predictions about the distribution of galaxy clusters across cosmic scales, confirmed. The model worked. Scientists defended it with confidence because the data kept agreeing with it. Webb changed the confidence level. The model makes specific predictions about how galaxies form over time. It predicts a gradual buildup, small structures first, then larger ones, building hierarchically as gravity does its slow work across billions of years. The earliest period of the universe, the model says, should contain only the seeds of structure, the first collapsing gas clouds, the first faint proto-galaxies, objects that will eventually become full galaxies hundreds of millions to billions of years later. Webb looked at that era and found the finished buildings before the construction crews had arrived. A researcher named Ivo Labe, part of a team analyzing Webb's early infrared data, described the situation bluntly in a published paper. His team identified galaxies so massive in the early universe that their existence exceeded what the Lambda CDM model produces, even under the most optimistic assumptions about early star formation. Confirmed, published in Nature, disputed by some, replicated by others. The dispute itself reveals something important. When a result this significant lands, two camps form immediately. One camp works to explain the observation within the existing model, stretching assumptions, adding efficiency factors, adjusting parameters. The other camp asks whether the model needs more fundamental revision. Both camps are doing legitimate science. Both have published serious work. What Webb did was force that argument into the open at a scale it had never reached before. The telescope provided enough data, clear enough and distant enough, to make the discrepancy undeniable. Before Webb, the earliest observable galaxies were fuzzy, ambiguous, hard to characterize precisely. Webb made them sharp. It made their mass measurable. It made their age confirmable through spectroscopy. And sharp, measurable, confirmed data is the thing that ends scientific comfort zones. The Lambda CDM model remains the leading framework. Scrapping it entirely would require evidence far beyond what any single telescope can produce. But the confidence that surrounded it, the certainty that its timeline of cosmic history was essentially correct, took a direct hit. Several leading cosmologists began using language in interviews and papers that they had carefully avoided for years. Language about the model being incomplete, about needing new physics, about the possibility that the conditions immediately after the Big Bang operated by rules we have not yet identified. That is a significant shift in scientific tone. And Webb had only been operating for a matter of months. What the telescope detected next moved the conversation from galaxy formation into the machinery of time itself, and the revelations there made the galaxy problem look almost manageable. How Webb reads the age of light. Webb does not just see distant objects, it reads them. And the reading method is one of the most elegant tricks in all of science. Light carries information. Every element in the universe, hydrogen, helium, carbon, oxygen, absorbs and emits light at specific wavelengths. These wavelengths act like fingerprints. When astronomers analyze the light from a distant star or galaxy, they can identify exactly which elements are present by matching those fingerprints to known patterns. This technique is called spectroscopy, and it has been the backbone of astrophysics for over a century. Webb's instruments perform spectroscopy with a precision and range that no previous telescope could match. Its infrared sensitivity allows it to read the fingerprints of objects so distant that their light has been traveling toward us since the universe was a fraction of its current size. Here is where time enters the picture. As the universe expands, space itself stretches. Light traveling through expanding space gets stretched along with it. A wave of light that started its journey as ultraviolet radiation, with short, energetic wavelengths, arrives at Webb billions of years later as infrared radiation with long, stretched wavelengths. Astronomers call this redshift. The more stretched the light, the greater the redshift. The greater the redshift, the older the light. The older the light, the farther away and further back in time the object that sent it. Webb measures redshift with extraordinary accuracy. By reading the spectroscopic fingerprints of distant galaxies and comparing their wavelengths to known values, scientists calculate exactly how much the light has stretched during its journey. From that stretching, they calculate distance. From distance, they calculate time. A galaxy at a redshift of about 8 corresponds to light that left it when the universe was roughly 600 million years old. A galaxy at a redshift of 13 corresponds to light from less than 350 million years after the Big Bang. These are confirmed measurements, confirmed through multiple spectroscopic observations, cross-checked against independent methods. Before Webb, astronomers could estimate redshifts using color alone, a rougher technique called photometric redshift. It worked reasonably well, but carried significant uncertainty. You could identify a galaxy as probably ancient, but pinning down its exact age required spectroscopy, and the faintest, most distant galaxies were too dim for any instrument to read cleanly. Webb changed that. Its light-gathering power is sufficient to perform spectroscopy on galaxies that Hubble could barely detect at all. Webb does not just spot ancient light, it reads ancient light. It identifies what those early galaxies were made of, how fast their stars were forming, whether they contained heavy elements forged in stellar explosions, and how those elements compare to younger galaxies. The results from that chemical reading carried their own surprises. Several of the earliest galaxies already contained heavy elements: carbon, oxygen, silicon, elements that only form inside stars and get dispersed when stars die. Their presence in such early galaxies means those galaxies had already lived through at least one full generation of stellar birth and death before the universe reached its first billion years. An entire generation of stars born, burned, and exploded, all before the timeline said there was enough time for stars to form in the first place. Webb's redshift readings did not just place these galaxies in time. They revealed that time in the early universe was somehow more productive than we calculated. And one galaxy in particular put a sharp point on exactly how extreme that productivity had become. The galaxy at the edge of everything. There is a confirmed object in Webb's data that sits at the farthest distance any galaxy has ever been spectroscopically confirmed. Its catalog name is technical and long, so scientists and science communicators have taken to calling it simply the record holder, or by a shortened designation. For our purposes, call it the early giant. And the early giant is extraordinary. Its light left it when the universe was approximately 320 million years old. The universe today is about 13.8 billion years old. That means we are looking back across more than 13 billion years of cosmic time. The light traveling from that galaxy to Webb's mirrors has been in transit since an era so remote that our star, our planet, and every element heavier than helium in our bodies did not yet exist anywhere in the cosmos. And when Webb read that light, it did not find a faint smear of gas. It found structure, coherent stellar populations, a galaxy that was already, by any reasonable measure, a mature system. The confirmation came through spectroscopy. Scientists identified specific chemical fingerprints in the galaxy's light and cross-referenced its redshift against multiple independent measurements. The result held. The galaxy's distance and age are confirmed to a high degree of scientific confidence. What makes the early giant particularly difficult to explain is its stellar mass. The stars inside it, totaled together, represent a quantity of matter that took our own galaxy billions of years to accumulate. But the early giant had only a few 100 million years to work with. In cosmological terms, that is barely a rounding error. To accumulate that much stellar mass in that time frame, the galaxy would have needed to convert gas into stars at a rate far above anything observed in the modern universe. Scientists call this star formation efficiency, and in today's galaxies, it is relatively low. Most gas in a galaxy at any given moment is not actively forming stars. Turbulence, radiation pressure from existing stars, supernova explosions, all of these disrupt the collapse of gas clouds and slow the process. In the early giant, either those disruptions were absent, or something was suppressing them, or some other mechanism we have not identified was accelerating the process to a degree our models consider improbable. One possibility that gained traction in published papers is that the very first stars in the universe, called Population 3 stars, were so massive and so short-lived that they seeded the early cosmos with heavy elements almost immediately after formation. That rapid seeding could have triggered faster, more efficient secondary star formation in the gas clouds around them, kick-starting galaxies before the standard timeline expected them. Population 3 stars are confirmed theoretically. Their existence is predicted by well-established physics. Webb is actively searching for direct evidence of them. So far, possible detections have been reported, but none confirmed to the same standard as the early giant itself. The early giant stands as confirmed. Its implications remain open, and it is one data point among dozens Webb has already produced. Each new data point from that era tells the same story. The early universe was building things faster, at scales larger than the model expected. And somewhere in that compressed early history, something even harder to explain was taking shape. Something that was not supposed to exist yet either. Something dark, something massive, and something that may have come before the galaxies themselves. The mass that cannot exist. The galaxies were one problem. The black holes were another problem entirely. Supermassive black holes sit at the center of most large galaxies. Ours has one. It masses about 4 million times more than our star. Nearby galaxies have larger ones. The biggest known supermassive black holes in the modern universe measure in at billions of times the mass of a star like ours. We know how they grow. A black hole forms when a massive star collapses at the end of its life. That initial black hole, called a stellar mass black hole, might carry the mass of 10 to 100 stars. From there, it grows by consuming surrounding gas, dust, and occasionally other objects. When it feeds aggressively, it blazes as a quasar, one of the brightest objects in the cosmos. Over billions of years, Through feeding and mergers, these black holes grow to supermassive scales. The key phrase is over billions of years. Growth has a speed limit. A black hole feeding at its theoretical maximum rate, called the Eddington limit, can only double its mass on a timescale of tens of millions of years. To reach a mass of 1 billion stars worth of matter, starting from the collapse of a single massive star, even at maximum feeding rate, requires close to 1 billion years of continuous growth. Webb found supermassive black holes in the early universe that were already enormous, already at masses that should require close to 1 billion years to build, already sitting at the centers of those early massive galaxies that also should not have existed yet. The timescales compounded. To have those black holes ready, the universe needed to start growing them almost immediately after the Big Bang, within the first 100 million years, at a point when, according to the Standard Model, the first stars were only beginning to form. One confirmed detection from Webb's early data showed a supermassive black hole at the center of an extremely distant galaxy, actively feeding, blazing, and carrying a mass of hundreds of millions of stars. Its light arrived from an era less than 700 million years after the Big Bang. The standard maximum growth timeline from a single stellar collapse makes that mass essentially impossible in that time. Several explanations circulate in the scientific community. One proposal suggests the very first black holes formed directly from collapsing clouds of gas, bypassing the stellar phase entirely. These hypothetical objects, called direct collapse black holes, would start life already far more massive than anything formed from a dying star, giving them a head start on growth that could explain the observed masses. Direct collapse black holes are theoretically viable. They remain unconfirmed observationally. Another proposal involves dense clusters of early stars collapsing together, producing an initial black hole already thousands of times more massive than a standard stellar remnant. Again, theoretically sound, observationally unconfirmed. A third, more radical suggestion, with growing support in recent published papers, is that the standard Eddington limit may not have applied in the early universe. If conditions allowed black holes to feed far above the theoretical maximum for short periods, super-Eddington accretion, then the growth timelines compress significantly. All three proposals require physics operating in ways we have not directly observed. All three represent real, active areas of research. None has reached confirmed status. What is confirmed is the black holes themselves. Their mass, their location in time, their existence at a point when they had no right to be that large, and both the black holes and the galaxies surrounding them pointed toward the same unsettling conclusion. Whatever happened in the first billion years of the universe, it happened faster, harder, and more efficiently than everything we built our models on. What cosmic time actually means. Before going further, we need to slow down and look at something that sounds simple but reveals itself to be genuinely strange. Time. Specifically, cosmic time, and what it means to say we are watching the universe's past. When you look at anything, you are looking into the past. The light from an object takes time to reach your eyes. When you look at someone across a room, you see them as they were a tiny fraction of a second ago. When you look at the moon, you see it as it was roughly 1.3 seconds ago. When you look at our star, you see it as it was about 8 minutes ago. At cosmic distances, those delays become extreme. The nearest large galaxy to ours, the Andromeda Galaxy, sits about 2.5 million light-years away. The light reaching us from Andromeda right now left that galaxy 2.5 million years ago. At that moment in time, our ancestors were using stone tools. Andromeda as it exists today, right now, at this moment, is invisible to us. It will be invisible for 2.5 million years. Webb operates at distances where this effect is amplified to scales that reshape what the word observation means. When Webb photographs a galaxy 13 billion light-years away, it is recording an event that happened 13 billion years ago. The galaxy Webb sees may have merged with a neighbor 6 billion years ago. It may have changed completely. It may have been consumed. We have no way to know. We are watching a recording of something that finished playing out before our planet existed. This is a confirmed property of physics. Light travels at a fixed speed. The universe is large. Therefore, distance equals time when it comes to observation. Webb pushed the observational window further back than any instrument before it. Farther back means earlier in cosmic history, and earlier in cosmic history means closer to a period when the physics of the universe itself may have operated under different conditions than what we observe today. Here is what makes this genuinely strange for our understanding of time. The universe is expanding. Space between galaxies is stretching. This means that a galaxy 13 billion light-years away in the direction we are looking was much closer when it emitted that light. The universe was smaller. The light left from a shorter distance. And then, as it traveled, the space it was crossing expanded underneath it, stretching both the light itself and the effective distance it had covered. This means the concept of how far away something is becomes complicated at cosmic scales. There is light travel distance. There is the size of the observable universe versus the full universe. These numbers all differ significantly. Webb's observations forced cosmologists to sit with this complexity at an unprecedented level. The telescope's data points do not just tell us how old certain galaxies are. They tell us how the universe was evolving during the period when those galaxies formed. And the evolution Webb revealed was running at a pace that made scientists question whether the standard timeline of the universe's first billion years was measuring the right things with the right assumptions. And that question, whether our entire timeline needs recalibration, brought physicists to a confrontation with the Big Bang itself. Did the Big Bang happen the way we think? The Big Bang is the starting point of everything. Every atom, every galaxy, every second of time we can observe traces back to a single event roughly 13.8 billion years ago, when all the energy and matter in the observable universe occupied a space smaller than the period at the end of this sentence, and then expanded. That sentence, as familiar as it sounds, contains assumptions, and Webb's data began stress testing those assumptions in ways scientists had not anticipated. The Big Bang model itself is confirmed by multiple independent lines of evidence. The expansion of the universe is measured and real. The cosmic microwave background, the faint glow of heat left over from the early universe, matches theoretical predictions with extraordinary precision. The ratio of hydrogen to helium in the universe matches what the Big Bang predicts. The existence of the cosmic web, the vast network of galaxy filaments and voids that structures the large-scale universe, fits the model's predictions. So the Big Bang happened. That is not in question. What Webb is putting pressure on is the specific sequence of events in the first billion years after it. Standard cosmology includes a period called inflation, a brief and violent burst of expansion in the universe's first tiny fraction of a second. Inflation solved several problems with the original Big Bang model. It explained why the universe looks so uniform in all directions. It explained the origin of the tiny density fluctuations that gravity later amplified into galaxies and clusters. But inflation is a theoretical addition to the model. Its exact mechanics are unknown. The energy field that drove it, called the inflation field, has never been directly detected. And different versions of inflation theory predict different things about what the universe looked like immediately after inflation ended. Webb's observations of massive, structured early galaxies are now being used to test these inflation models against each other. Some models of inflation produce stronger density fluctuations than the standard version does, which would give gravity a head start on building structure. Those models could, in principle, explain the early massive galaxies Webb found. If a stronger fluctuation inflation model turns out to fit Webb's data better than the standard version, that would represent a major discovery. It would mean our map of the universe's first fraction of a second needs redrawing. A separate but related possibility is that dark matter, the invisible mass that makes up most of the universe's matter content, behaved differently in the early universe than in the modern era. If early dark matter clustered more aggressively, it could have accelerated galaxy formation without changing inflation theory at all. Both options remain genuinely open. Both are being actively investigated using Webb's data. Scientists are running simulations, comparing outputs to Webb's observations, and working to identify which model, or which combination of models, reproduces what the telescope found. The process is working as science should. An anomaly appears. Multiple explanations are proposed. Evidence is gathered to test them. The model that survives is refined. What is different this time is the scale of the anomaly, and the fact that Webb is only getting started. Because the era Webb opened up for observation, the first few 100 million years of cosmic time had a specific event at its heart that cosmologists call the cosmic dawn. And the cosmic dawn itself turned out to be even more layered and dramatic than the galaxy problem suggested. The cosmic dawn, the universe's first light switch. Imagine the universe going dark, completely dark, for tens of millions of years. After the Big Bang's initial fireball cooled, the universe became a fog. Hydrogen gas, neutral and opaque, filled everything. Light could not travel freely through it. Photons scattered endlessly off hydrogen atoms, unable to move in straight lines, unable to escape. The cosmos was a locked room with no exits for light. This era is called the Dark Ages, confirmed by cosmological theory, consistent with observations of the cosmic microwave background, lasting from roughly 380,000 years after the Big Bang until the first stars ignited, which current estimates place somewhere between 100 and 400 million years after the Big Bang. When those first stars turned on, something remarkable happened. They burned intensely. Almost all of the first stars were giants, far more massive than typical modern stars. They pumped out ferocious amounts of ultraviolet radiation, and that radiation began doing something to the surrounding hydrogen fog. It ionized it. Ionization means stripping electrons away from hydrogen atoms, turning neutral hydrogen into a plasma of charged particles. Charged hydrogen does not block light the same way neutral hydrogen does. As the first stars ionized the gas around them, they began carving out bubbles of transparent space. Inside those bubbles, light could travel freely for the first time. Over hundreds of millions of years, more stars formed. More bubbles expanded. The bubbles merged, and eventually, the hydrogen fog across the entire observable universe cleared. Light could travel freely across cosmic distances. The universe became transparent. This process is called reionization, and Webb is the first telescope capable of observing it directly. Before Webb, astronomers could infer that reionization happened from indirect evidence. The spectra of distant quasars showed the signature of neutral hydrogen absorption at certain redshifts, confirming that beyond a certain distance, the fog was still present. But they could not watch the individual bubbles form. They could not see the patchwork of ionized and neutral regions during the process itself. Webb can. Its infrared sensitivity at the right wavelengths corresponds exactly to the light signatures of reionization-era hydrogen. Early images and spectra from Webb have already shown evidence of individual ionized bubbles around early galaxies, regions where a galaxy's own ultraviolet radiation has burned away the surrounding fog for hundreds of thousands of light years in every direction. Scientists are using these detections to map the timeline of reionization more precisely. When did it begin? Which types of galaxies drove it? How many stars were required to clear the fog completely? Webb is providing data that is actively revising answers to all three questions. One confirmed finding already distinguishes Webb's observations from prior assumptions. The sources of reionization appear to be more numerous and smaller than expected. Earlier models predicted that large, bright galaxies did most of the ionizing work. Webb's data suggests that vast populations of faint, small galaxies contributed significantly, possibly more than the large, bright ones did. That revision matters. It changes the count of how many galaxies must have existed in the early universe and what they looked like. And a higher count of early galaxies feeds directly back into the mass problem from the earlier chapters, compounding the tension with the standard model. The cosmic dawn was brighter, earlier, and driven by more participants than the model expected. And the stars that started it all were unlike anything burning in the sky above you tonight. The first stars, giants that burned before everything. The first stars were monsters. Every star you can see with your eyes at night is a second, third, or later generation star. It formed from gas that had already been enriched by the deaths of earlier stars, gas laced with carbon, oxygen, silicon, iron, elements forged in stellar cores and blasted into space by supernova explosions across billions of years. The first stars had none of that inheritance. They formed from pure primordial gas, almost entirely hydrogen and helium, the only elements the Big Bang produced. And the absence of heavy elements changed everything about how they formed and how they burned. In modern star formation, Heavy elements in a gas cloud help it cool more efficiently. Cooling allows the cloud to collapse further before pressure stops the process, producing stars of moderate mass. Without heavy elements, the gas clouds in the early universe cooled far more slowly. Pressure resisted collapse longer. The result was gas clouds that had to accumulate far more mass before collapsing, producing stars of extraordinary size. Current theoretical models, confirmed by simulation and consistent with known physics, predict that the first stars ranged from about 10 times to possibly several hundred times the mass of our star. Some models suggest the very first stellar objects may have reached close to 1,000 solar masses, a scale that has no modern equivalent. Stars of that size burn through their nuclear fuel at a catastrophic rate. A star 100 times the mass of ours burns roughly 1 million times brighter and lives for perhaps 2 million years. Our own star has a lifespan of about 10 billion years. These first stars were cosmic mayflies, born enormous, burning furiously, and dead within a fraction of a percent of our star's lifetime. Their deaths were equally extreme. Stars above a certain mass threshold do not end in standard supernovae. They detonate in what are called pair instability supernova, explosions so energetic that they may leave no remnant behind at all, or they collapse directly into black holes without exploding outward. Either way, they seed the surrounding gas with the first heavy elements the universe had ever seen. Those heavy elements, scattered across light years of space by the dying first stars, seeded the second generation of star formation. Gas enriched with even trace amounts of carbon and oxygen, cooled more efficiently. Smaller, longer-lived stars could form. The universe's stellar population diversified. Webb has not confirmed the direct detection of first-generation stars yet. They are one of the telescope's primary scientific targets. Candidate detections have been reported in a few publications, including a galaxy cluster studied in 2023, where certain light signatures suggested the presence of extremely metal-poor stars consistent with early-generation chemistry. Those reports are not yet confirmed to the level of the galaxy detections, but the gravitational legacy of the first stars is confirmed in Webb's data. The chemical signatures in early galaxies that Webb can read spectroscopically show patterns consistent with enrichment from massive, short-lived early stars. The fingerprints of those giants are embedded in every galaxy that came after them, and one of the most immediate consequences of those dying first-star giants was the seeding of the universe's first black holes, objects that grew on a timeline that still does not fully add up. But there is something Webb found that complicates even that story, something suggesting the black holes themselves may have arrived before the galaxies that contain them, challenging the entire assumed sequence of cosmic construction. Black holes that came first. For decades, the assumed relationship between galaxies and their central black holes worked like a building and its foundation. First the structure, then the basement. Stars formed, gas collapsed, galaxies grew, and at their dense centers, black holes accumulated and eventually grew supermassive, feeding on the material flowing inward. Webb's observations suggest the sequence may be reversed, in at least some cases. Multiple early galaxies in Webb's data show a pattern that challenges the building first model. Their central black holes are disproportionately massive compared to the galaxies surrounding them. In the modern universe, supermassive black holes and their host galaxies maintain a relatively consistent size ratio. The black hole typically represents a small fraction of the galaxy's total stellar mass. The ratio is tight enough that astronomers built a confirmed empirical relationship around it. In Webb's early universe galaxies, that ratio is broken. The black holes are too large relative to the galaxies they sit inside. The black holes look like they formed and grew before the surrounding galaxy had time to fully assemble. One confirmed and peer-reviewed study, published after Webb's first year of science operations, analyzed a set of early active black holes and found their masses ran roughly 10 times higher relative to their host galaxies than the same ratio. In modern galaxies, 10 times, the relationship that held across billions of years of cosmic history appeared to dissolve in the early universe. This has two possible explanations, both serious and both with published support. The first is that black holes in the early universe grew faster than their surroundings simply because the conditions were right for rapid feeding. Dense gas, frequent mergers, chaotic environments. The galaxies eventually caught up as more stars formed. The black holes just had a head start. The second explanation is more radical. Some theorists argue that in at least some regions of the early universe, the black hole came first entirely. A direct collapse black hole formed from an enormous gas cloud, grew rapidly, and its gravitational influence and energetic feeding actually triggered the star formation that built the surrounding galaxy around it. The black hole did not sit inside the galaxy. The galaxy grew around the black hole. This second model, sometimes called the black hole first scenario, is theoretically supported and consistent with at least some of Webb's observations. It remains unconfirmed as a dominant formation pathway. But the data from Webb makes it a legitimate contender in a way it was not before the telescope launched. If the black hole first scenario is correct for a significant fraction of early galaxies, it means the entire framework for how large-scale cosmic structure assembles needs reordering. The scaffolding comes before the building. The anchor comes before the chain. Gravity concentrates first at the bottom, then structure grows upward around it. That reordering has consequences that ripple beyond galaxy formation. It touches the question of how supermassive black holes became so massive so quickly. It potentially explains why the early galaxies Webb found were already so structured. And it raises a question that currently has no confirmed answer. If black holes seeded galaxy formation in the early universe, what seeded the black holes? Webb is already gathering the data that may eventually answer that question. And as it does, it is simultaneously watching a process that the first stars and first black holes triggered together, a process that transformed the entire universe from an opaque fog into the transparent cosmos we inhabit. Watching the universe go clear, picture fog so thick you cannot see your hand in front of your face. Now picture a lantern switching on inside it. A small sphere of clarity opens around the light source. You can see a few feet in every direction. The fog beyond that sphere remains impenetrable. Now picture millions of lanterns switching on across an area the size of a continent. Their spheres of clarity expand, touch, merge. One by one, the patches of fog clear, until, eventually, the entire area is transparent and you can see from one end to the other. That is what reionization looked like across the observable universe, and Webb is capturing it. The fog, as established earlier, was neutral hydrogen filling the space between the earliest galaxies. The lanterns were those early massive stars, burning intensely enough to ionize the surrounding gas. Webb's job in this observation is to map the bubbles, to identify where, when, and how quickly the fog cleared in different regions. A confirmed result from Webb's first 2 years of data concerns the patchiness of reionization. Earlier models assumed the process was relatively smooth, with the fog clearing at a similar rate across large volumes of space. Webb's data showed something messier. Reionization was highly uneven. Some regions cleared early because they happened to contain dense concentrations of early galaxies. Other regions, galaxy-poor voids, stayed fogged for hundreds of millions of years longer. This uneven clearing is now confirmed across multiple independent datasets from Webb. It has direct consequences for how we count early galaxies and estimate the total ultraviolet radiation output of the early universe. The numbers needed revising. A separate and striking observation came from Webb's spectroscopy of light passing through the reionization era fog. Specific wavelengths of light get absorbed by neutral hydrogen. By measuring which wavelengths are missing from the light of distant objects, astronomers can calculate how much neutral hydrogen that light passed through. Webb performed this measurement on multiple distant quasars, objects bright enough to serve as backlit probes of the early universe's gas, and confirmed that the neutral hydrogen fraction in the universe dropped sharply and rapidly during a specific period, somewhere between 500 million and 1 billion years after the Big Bang. That sharp drop is the fog clearing. Confirmed. What surprised scientists was the speed of the clearance in certain regions. Some areas went from heavily fogged to nearly transparent within what appears to be a relatively short cosmic time frame, suggesting bursts of intense star formation pumping ultraviolet radiation into the surrounding space faster than earlier estimates predicted. This connects to the galaxy mass problem from the earlier chapters. If early galaxies were forming stars at extraordinary rates, those rates would also produce extraordinary amounts of ionizing radiation. The same efficiency that built massive galaxies fast also cleared the cosmic fog fast. The two anomalies reinforce each other. Both point towards early universe conditions that were more extreme than the model anticipated. Webb is still mapping. The reionization history of the universe is one of the telescope's core science programs, and data continues to come in with each observing cycle. Scientists expect a comprehensive reionization timeline, significantly more detailed than anything produced before Webb, within the telescope's first decade of operation. Inside that same era, Webb was also making observations closer to home, observations that moved the story from the ancient history of the cosmos to the immediate question of where life might exist in the universe today. Water found on a world 140 light-years away. In July 2202, Webb pointed at a planet circling a distant star and found water. Confirmed. Peer-reviewed. Published in Nature. Water vapor in the atmosphere of a planet called WASP 96b, orbiting a star about 1,000 light-years away. The detection itself required no exotic technology beyond what Webb already had. As the planet passed in front of its star, a tiny fraction of the star's light filtered through the planet's atmosphere on its way to Webb's sensors. Different molecules in the atmosphere absorbed different wavelengths of that light. Webb's spectrograph captured those missing wavelengths, and among the signatures embedded in the absorption pattern were the unmistakable chemical fingerprints of water vapor. Simple in principle, extraordinary in execution, and only possible because Webb's infrared sensitivity and light-gathering power operate at a level no previous telescope achieved. Now, WASP 96b is not a candidate for life. It is a hot gas giant roughly half the mass of Jupiter, orbiting very close to its star, and therefore baking at temperatures that would vaporize most materials. The water in its atmosphere is a chemical fact, not a biological signal. Scientists made this clear immediately, but the detection mattered for reasons beyond the specific planet. Before Webb, detecting molecules in exoplanet atmospheres was difficult, imprecise, and limited mostly to the largest and hottest planets where signals were strongest. The data often came with significant uncertainty. Webb demonstrated that it could cleanly, confidently, and, in a relatively short observation time, read the atmospheric chemistry of planets with a resolution and sensitivity that makes detailed study possible. That capability, applied to the right planets, changes what is scientifically achievable in the search for life. WASP 96b was a demonstration, a proof of concept. Scientists already knew hot Jupiters could have water. Confirming it through Webb was valuable not because it surprised anyone about WASP 96b specifically, but because it showed the method works with the clarity needed to detect far subtler signals in far more interesting atmospheres. The immediately more interesting planets are small, rocky ones orbiting in the habitable zone of their stars, the range of distances where liquid water could exist on a surface. Webb cannot currently detect atmospheric chemistry in Earth-sized rocky planets around Sun-like stars with its full sensitivity, but it can study rocky planets around smaller, cooler stars, called red dwarfs, where the geometry is more favorable. And in the months following the WASP 96b announcement, Webb began turning its instruments toward exactly those systems. One system in particular had been waiting since its discovery in 2017. 7 rocky planets, all orbiting a single red dwarf star about 40 light-years away, with several of them sitting inside the habitable zone. Scientists considered it one of the most promising systems for atmospheric characterization within reach of Webb. Webb started studying those planets, and what it found there, or more precisely what it failed to find, told a story of its own that raised new questions about what a habitable world actually looks like. Carbon dioxide, chemistry, and the hunt for biosignatures. Reading a planet's atmosphere from 100 light-years away sounds impossible. Webb makes it merely very difficult. The technique is the same as the water detection. A planet passes in front of its star. Starlight filters through the atmosphere. Different molecules steal different wavelengths. Webb reads the gaps. Match the gaps to known chemical fingerprints, and you know what the atmosphere contains. Carbon dioxide was the next confirmed detection, announced in August 2000 for the hot gas giant WASP 39b, orbiting about 700 light-years away. Webb detected carbon dioxide in its atmosphere with a signal clearer than any previous exoplanet chemistry observation. Confirmed, peer-reviewed, published. Carbon dioxide matters because it is one of the molecules that Webb's instruments can detect with high confidence across a range of planet types. In the hot Jupiter context, it is primarily a chemical benchmark, confirmation that Webb's atmospheric spectroscopy works as designed. But carbon dioxide is also one of the molecules on the biosignature checklist. On Earth, living organisms produce carbon dioxide as a metabolic byproduct. Its presence alongside other specific molecules, particularly oxygen, methane, and nitrous oxide, in ratios that chemistry alone cannot easily maintain, would constitute a potential biological signal. A biosignature is any molecule, pattern, or condition that living processes produce, and that abiological processes are unlikely to explain. The concept sounds straightforward. The detection challenge is enormous. The difficulty is false positives. Volcanoes produce carbon dioxide. Certain chemical reactions produce methane without biology. Oxygen can accumulate through photochemical processes that have nothing to do with photosynthesis. Each potential biosignature molecule has non-biological sources that must be ruled out before life becomes a credible explanation. This is why scientists look for combinations. A single molecule is ambiguous. Multiple molecules coexisting in ratios that require a living system to maintain them is far more compelling. The most discussed combination is called the biosignature gas disequilibrium. The presence of molecules like oxygen and methane together in an atmosphere where they would normally react with each other and destroy each other unless something was continuously replenishing both. Earth's atmosphere is in exactly that kind of disequilibrium. Oxygen and methane coexist here because life produces both continuously. Without life, they would react, and one of them would disappear within geological timescales. Webb is years away from reading that specific combination in a rocky planet atmosphere. The signal-to-noise challenge for small planets is significant, and dozens of transit observations are needed to build a clear picture. But the trajectory is confirmed. Webb's sensitivity and spectral range cover the relevant molecular signatures. The question is time and targeting. The targeting decisions happening right now in telescope scheduling meetings will determine which planets get enough observation hours to attempt a full atmospheric characterization. Those decisions are being made based on which planetary systems offer the best geometry, the clearest stellar background, and the most favorable planet-to-star size ratios. And somewhere in that list of targets, scientists believe may be a world with an atmosphere that does not add up. One whose chemistry tells a story that chemistry alone cannot write. Webb has not found that signal yet. Every scientist working on this program knows it may take years more, but the tools are confirmed, the sensitivity is there, and the next chapter of this search began with an image that changed how every person on Earth thinks about the scale of the cosmos. What a biosignature would actually mean. Before the deep field image, pause here. Because the biosignature question deserves its own space, and the weight of what its detection would mean is larger than most people allow themselves to consider. Webb finding water on a hot gas giant created headlines. Webb reading carbon dioxide in a distant atmosphere generated scientific papers. A confirmed biosignature detection on a rocky planet in a habitable zone would be categorically different from anything that has happened in the history of science. Every civilization that has ever looked at the night sky has asked the same question. Are we alone? Philosophy, religion, literature, and science have circled it for thousands of years without a confirmed answer. Detecting a biosignature would not answer the question completely, but it would move the probability from unknown to likely. And that shift would be the largest revision in human self-understanding since Copernicus moved Earth out of the center of the cosmos. Consider what it would confirm. Life is not a fluke specific to Earth. It is a phenomenon that the chemistry of the universe produces wherever conditions allow. If life exists on a rocky planet 40 light-years away, orbiting a dim red star with a completely different evolutionary history than Earth's, then the universe is probably full of it. The logic is simple. If it happened twice in one small neighborhood of one galaxy, it is a universal process. That realization would reach beyond science. Every question about humanity's significance, Every assumption about what is unique to our planet, every calculation about the probability of encountering another mind in the cosmos, would need revision. Webb cannot yet make a confirmed biosignature detection. Current estimates from the scientific community suggest that studying the best candidate rocky planets in nearby red dwarf systems will require somewhere between 50 and 100 transit observations per planet, spread across multiple years. For a confirmed detection requiring multiple corroborating molecules, the timeline extends further. Several candidate systems are actively being studied. The 7-planet system around the dim red dwarf star 40 light-years away, whose planets scientists have labeled by letter designations, received Webb observation time in its first operational year. Results have been cautious. One of the inner rocky planets showed no evidence of a thick atmosphere, which may indicate it is more Mars-like than Earth-like, stripped of air by stellar radiation. That result was confirmed and published. The outer planets in that same system have received less observation time and remain less characterized. Webb schedulers allocate time carefully, and atmospheric characterization campaigns for rocky exoplanets compete for hours against galaxy surveys, stellar nursery imaging, and solar system observations. But the campaign is running. The program is funded. The instruments are confirmed capable of the task. The biosignature search is a years-long effort, but every transit observation Webb completes of a rocky habitable zone planet adds data. Every atmospheric spectrum it captures narrows the uncertainty. And somewhere in the accumulating data from this telescope, or from the next generation of instruments it is already informing, the answer to humanity's oldest question may be quietly taking shape. That question is not going anywhere. And Webb is not finished looking. What it showed us next had nothing to do with nearby planets. It pointed outward, all the way outward, into the deepest dark that human instruments had ever recorded. 45,000 galaxies in a grain of sand. The first deep field image from Webb arrived on July 12, 2002. It covered a patch of sky smaller than a grain of sand held at arm's length. Inside that patch, more than 45,000 galaxies, each one a complete galaxy, hundreds of billions of stars, potentially hundreds of billions of planets, spread across billions of years of cosmic time, all compressed into a single image that takes less than a second to see in full. The image is confirmed real. Every point of light that is not a star in our own galaxy is a separate galaxy. Many of the faintest, reddest smears in the image are confirmed by Webb spectroscopy to be among the most ancient objects ever recorded, their light traveling for over 13 billion years to reach the detector. Webb produced this image through 21 hours of exposure time. Its predecessor, Hubble, produced a comparable deep field image in the 1990s, but required 11 days of exposure to capture a similar patch of sky, and at lower resolution. Webb did it in under a day, at sharper resolution, reaching further back in time. The 45,000 galaxies visible in that single image are a sample, an infinitesimally small sample of the full observable universe. Extrapolate the galaxy density in that image across the full sphere of the observable cosmos, and the estimates for the total number of galaxies reach into the hundreds of billions, possibly more than 2 trillion, when smaller, fainter galaxies are included. 2 trillion galaxies, each containing hundreds of billions of stars. And Webb is finding that many of those galaxies, including the earliest and most distant ones, are larger, more massive, and more structured than the model predicted. The scale of what that implies takes a moment to process. The human brain did not evolve to handle numbers like 2 trillion. It has no intuitive grip on it. But the deep field image does something that numbers cannot. It makes the scale visible. You can look at it. You can let your eyes move from one small smear of light to another and understand, in the way that images communicate differently from numbers, that every one of those smears is a galaxy, a complete, ancient, enormous system of stars. Several of the galaxies visible in the deep field appear distorted, stretched into arcs, or duplicated into multiple images. That distortion is gravitational lensing, the gravity of massive galaxy clusters in the foreground, bending the light of more distant galaxies behind them, magnifying and warping their appearance. Webb sensitivity makes those lensed arcs sharper than any previous instrument could resolve. And that lensing effect, beyond its visual drama, is a scientific tool. The degree of distortion reveals the mass of the foreground lens. Webb is using gravitational lensing systematically across dozens of galaxy clusters to map dark matter distributions and peer even deeper into the early universe than direct imaging alone allows. The deep field image was a statement, a visual proof that the observable universe is incomprehensibly full. And hidden inside the light of the oldest objects in that image were signals that, when decoded, revealed something about the universe's structure that no one had fully anticipated. The next tool Webb deployed to reach even further was not a new instrument, it was gravity itself. Using gravity as a telescope, Webb is the most powerful space telescope ever built. And scientists figured out how to make it even more powerful by borrowing from the universe itself. Gravity bends light. Einstein predicted this in 1915, and it was confirmed 4 years later, during a solar eclipse, when astronomers measured starlight curving around our star exactly as the theory predicted. That bending effect, applied at cosmic scales, produces something extraordinary. A massive object, a galaxy cluster containing hundreds of trillions of solar masses of material, bends the light of everything behind it. It acts as a lens. This is called gravitational lensing, and Webb uses it deliberately. The geometry works like this. Webb points at a foreground galaxy cluster. Behind that cluster, at a much greater distance, sit fainter galaxies that Webb might not be able to resolve directly. The cluster's gravity curves the light from those background galaxies around it, redirecting paths that would otherwise miss Webb's mirror entirely. The result is multiple magnified images of the background galaxies, often stretched into arcs, sometimes duplicated into rings, or multiple copies arranged symmetrically around the lens. The magnification factor varies depending on the mass of the lens and the geometry of alignment. In the strongest cases, gravitational lensing amplifies background objects by factors of 10, 50, or even 100 times. This effectively extends Webb's reach into regions of the early universe that would otherwise remain invisible, even to its instruments. Webb's Cosmic Cliffs image, one of its early iconic releases, used lensing to reveal star-forming regions with detail that no prior telescope achieved. Its deep field also used the galaxy cluster Abell 274-7 as a natural lens, and within that lensed field, Webb identified galaxies whose distances were subsequently confirmed by spectroscopy to place them among the most ancient objects ever observed. The masses revealed through lensing analysis carry their own information. The degree of arc distortion in a lensed image encodes the total mass of the lensing cluster, including the dark matter component. Dark matter emits no light, but its gravitational influence bends light, just as normal matter does. By measuring how strongly a cluster lenses background galaxies, Webb can map the dark matter distribution inside the cluster with precision that direct observation can never achieve. Several Webb lensing studies have already produced dark matter maps of foreground clusters, revealing structures in the invisible mass that do not always align neatly with the visible galaxies. Clumps of dark matter exist where few visible galaxies sit. Regions dense with galaxies sometimes show less dark matter than expected. These misalignments are confirmed and are generating new theoretical work about how dark matter and normal matter interact or fail to interact during cluster formation and merging. The lensing program also acts as a discovery machine because the magnified background fields behind massive clusters are rich with ancient, faint galaxies that would be undetectable without the amplification. Webb's lensing surveys are producing new record distance objects on a regular basis. Several of the most distant confirmed galaxies in Webb's catalog were found in lensed fields, their light amplified by intervening clusters, to a level where spectroscopic confirmation became possible. Gravity itself, the oldest force in the cosmos, turned into an extension of the most advanced telescope humanity has ever built. And within those magnified ancient fields, Webb found something about galaxy structure that pushed the timeline problem into even more uncomfortable territory. A galaxy that already lived multiple lives. Among the most distant confirmed galaxies in Webb's catalog sits one that tells a story that should not be possible given its age. Its light left it when the universe was roughly 350 million years old. At that distance and age, the expectation was simple: a primitive structure, young stars, raw gas, the early chaos of a galaxy still assembling itself, a cosmic infant. Webb's spectroscopy told a different story. The galaxy's light contained the chemical signatures of old stellar populations, stars that had already evolved through their full life cycles and died. The presence of those chemical signatures means the galaxy had already been through at least one full round of star formation, stellar aging, and stellar death before the universe reached its first 400 million years. A full stellar generation in an early small galaxy might cycle through in tens to hundreds of millions of years for the most massive stars. That still leaves almost no margin. For a galaxy to show mature stellar chemistry at 350 million years after the Big Bang, star formation inside it must have begun extraordinarily early, progressed at extraordinary rates, and already produced multiple waves of stellar births and deaths. The galaxy appeared, in spectroscopic terms, older than its address in time allowed. Scientists examining this and similar objects in Webb's early dataset coined a term that has since appeared in multiple published papers: overmature galaxies. Systems whose chemical and structural complexity exceeds what the standard model produces at their confirmed age. Several explanations are proposed. The leading candidate involves the same accelerated star formation efficiency discussed in earlier chapters, here compounded by the possibility that the very first galaxies formed in regions of the early universe that were unusually dense. Where gas was abundant, mergers were frequent, and the raw material for stellar birth was essentially unlimited. A dense early environment could explain the acceleration. More gas means more stars. More stars means faster chemical enrichment. Faster chemical enrichment means the galaxy's stellar population ages chemically at an accelerated rate relative to its calendar age. The galaxy is young in time, but old in chemistry, because it lived fast. This pattern, if confirmed across a larger sample of early galaxies, would suggest that the first cosmic structures formed preferentially in the densest knots of the early cosmic web, regions where matter concentrated earliest and most aggressively, and those dense knots would correspond to the seeds of what eventually became the largest structures in the universe, the great clusters and superclusters that define the large-scale architecture of the cosmos today. Webb is building that map. The overmature galaxy is one confirmed data point. As Webb accumulates more spectroscopic profiles of early galaxies, the picture of where and how the first cosmic structures formed is becoming sharper, more detailed, and more surprising with each observing cycle. And within that picture, a specific tension was growing, one that connected Webb's early universe observations to a decades-old problem in cosmology that the telescope was supposed to resolve but instead made significantly worse. The dark matter discrepancy. Dark matter is the universe's most important missing piece, confirmed to exist through its gravitational effects on visible matter, confirmed through galaxy rotation curves, gravitational lensing, and the large-scale structure of the cosmic web, yet confirmed to be invisible at every wavelength of light ever measured. The standard picture of dark matter, called cold dark matter, describes it as slow-moving particles that do not interact with light or normal matter except through gravity. This model predicts specific things about how dark matter distributes itself inside galaxies. It predicts that dark matter should pile up densely at galactic centers, in what theorists call a cusp, a sharp central peak of density. And it predicts that galaxy rotation curves, the speed at which stars orbit their galactic centers at different distances, should follow a specific pattern determined by that distribution. In the modern universe, observations of galaxy rotation curves have confirmed that dark matter exists, because galaxies rotate far too fast at their outer edges for visible matter alone to explain. But the detailed shape of that rotation has long presented complications. Many observed galaxies rotate in ways suggesting a central dark matter distribution that is flatter and more spread out than the cusps the cold dark matter model predicts. This discrepancy is called the core cusp problem, and it has been a known tension in cosmology for years. Webb brought it into the early universe. Several early galaxies in Webb's dataset show rotation patterns that do not match the cold dark matter predictions, even after accounting for the different conditions in the early universe. A team analyzing Webb's kinematic data from early high-redshift galaxies published results showing that some of these early systems rotate in ways more consistent with a dark matter distribution that is smoother and more centrally depleted than the standard model produces. This is a confirmed observational result. The interpretation remains debated. One camp argues the discrepancy reflects the influence of normal matter feedback. When massive stars explode as supernovae, they drive gas outward from galactic centers. That gas movement can gravitationally pull dark matter outward too, flattening the central cusp into a core. The process is called baryonic feedback, and it can, in principle, explain the observed rotation patterns without modifying the dark matter model itself. Another camp argues that the discrepancy is too large and too systematic to be fully explained by feedback, and that the cold dark matter model needs a fundamental revision. Proposals include warm dark matter, particles that move fast enough to erase small-scale structure, or fuzzy dark matter, an ultralight particle that behaves quantum mechanically on galactic scales and naturally produces flatter central distributions. Webb's early universe observations add urgency to this debate because the early galaxies Webb is studying existed before the long history of supernova feedback that shapes modern galaxies. If early galaxies show the same core cusp discrepancy despite having had less time for feedback to act, that weakens the feedback explanation and strengthens the case for a modified dark matter model. The results are preliminary across the full early galaxy sample. More observations are needed. The debate will not resolve quickly, but Webb has already made clear that the dark matter tension is present in the early universe, not just the modern one. And if dark matter is more complex than the cold dark matter model describes, that complexity would propagate through every calculation of galaxy formation, cosmic structure, and cosmic timeline. Every number would shift. Every date in cosmic history would need rechecking. Meanwhile, in a completely different observing mode, Webb was producing images of something far closer and far more visually immediate, the places where new stars are being born right now. Watching stars being born in real time, 4,000 light-years from Earth, inside a region of our galaxy called the Carina Nebula, stars are forming right now. Webb photographed it. And the image it produced changed what astronomers thought they knew about the birth process of stars. The Carina Nebula is one of the largest and brightest nebulae in our galaxy, a region of dense gas and dust where the gravity of the material causes it to collapse into dense cores, which then heat up and ignite as stars. The process has been studied for decades, but until Webb, astronomers were looking at it through a curtain. Visible light cannot penetrate the dense dust clouds that wrap around stellar nurseries. Hubble's images of Carina, beautiful as they were, showed only the surfaces of those dust clouds, illuminated from outside by the young stars already burning within. The actual nurseries, the dense cores where new stars were actively forming, were hidden. Webb's infrared vision removed the curtain. For the first time, astronomers could see directly into the formation zones. Individual protostars, objects in the process of collapsing from gas clouds into stars, appeared in Webb's images as distinct, resolved sources. Outflows of gas and jets of material ejected from forming stars appeared in sharp detail, their structure traceable across distances of several light-years. Hundreds of previously unknown protostars appeared in Webb's first Carina Nebula images. Hundreds. Objects that Hubble had missed entirely because they were embedded behind layers of dust that infrared light passes through and visible light does not. This had immediate consequences for the census of star formation in our galaxy. If the Carina Nebula alone contains hundreds of forming stars that previous instruments missed, the total star formation rate estimates for the Milky Way likely need upward revision. The galaxy may be building new stars faster than the previous census suggested, but the more scientifically significant finding came from the jets and outflows. Webb resolved in detail. Young protostars eject material along their rotation axes as they form. These jets are energetic, fast, and chemically rich. Webb's spectroscopy of those jets revealed complex organic molecules embedded in the outflowing material, molecules containing carbon and hydrogen chains that are precursors to the kinds of chemistry relevant to life. confirmed detection of complex carbon chemistry in the jets of forming stars. Published. Peer-reviewed. The implication is that the raw materials of organic chemistry are present at star formation itself. They are not delivered to planetary systems later from external sources. They are built into the system from the very beginning, emerging from the collapse process that creates both the star and the disk of material that will eventually form planets. This reframes how scientists think about the origin of organic chemistry in planetary systems. The chemistry does not arrive after the fact. It is part of the birth. And when Webb turned its attention from forming stars to forming planets, it found a timeline for planetary assembly that was equally surprising. The chemistry hidden inside a dying star, Webb did not only watch births, it watched death. And death, it turned out, is where some of the universe's most important chemistry happens. A star roughly 8 times the mass of ours, or smaller, ends its life by shedding its outer layers in an expanding shell of glowing gas, called a planetary nebula. The name is a historical accident. These structures have nothing to do with planets. They are the last breath of a dying star, its outer atmosphere blown outward over thousands of years while the hot core, a white dwarf, remains behind, blazing ultraviolet radiation into the expanding shell and causing it to glow in extraordinary colors. Webb photographed several planetary nebulae in its first years of operation. The images were visually stunning. But more important than the aesthetics was what the spectroscopy revealed inside those shells. The Southern Ring Nebula, one of Webb's early targets, sits roughly 2,000 light-years away. 2 stars sit at its center, one still bright and one a faint white dwarf, the actual progenitor of the nebula. Webb's infrared vision resolved both stars clearly for the first time and revealed the chemical content of the expanding shell with unprecedented detail. Inside the shell, complex molecules, polycyclic aromatic hydrocarbons, large carbon ring structures that are among the most common organic molecules in the universe, confirmed in the spectroscopic data from the Southern Ring Nebula. These molecules form in the cooling outer layers of evolved stars as they shed material and are then blasted outward into the surrounding interstellar space by the dying star's radiation and stellar wind. From there they travel. They mix into the gas clouds of the interstellar medium. They become part of the raw material from which the next generation of stars and planets forms. This means that every planetary system forming in our galaxy today is forming from gas that contains complex carbon chemistry inherited from generations of dying stars. The organic molecules present in star-forming jets, which Webb confirmed in the Carina Nebula, trace back to this source. Planetary nebulae are chemical factories seeding the galaxy with the molecular building blocks that planetary systems inherit at birth. The confirmed presence of these molecules in a nearby planetary nebula is not a new concept. Scientists have known for decades that dying stars enrich the interstellar medium. What Webb added was the detail and clarity of exactly which molecules are present, in what quantities, and how they distribute through the expanding shell. That detail allows better modeling of how much organic chemistry reaches newly forming stellar systems and what state that chemistry is in when it arrives. The numbers are feeding into current models of planetary habitability, specifically the question of how chemically rich a planet's early environment might be, even before life has any opportunity to develop. Webb is observing multiple planetary nebulae across different distances and stellar ages. Each one adds data to a chemical map of the galaxy's organic inheritance, and that map connects directly to one of the most fundamental questions Webb is contributing to answering. How common are the conditions for life? But before that question could be addressed fully, Webb needed to observe something far more dynamic and far more immediate. A system where a planet is forming right now, around a young star, in real time. Planet formation is faster and more violent than we thought. Around a young star about 450 light-years from Earth, a disk of gas and dust is in the process of becoming a solar system. Webb watched it, and what the telescope revealed revised a timeline that planetary scientists had considered settled for decades. The system sits inside a star-forming region called Taurus, a well-studied nursery of new stars embedded in an enormous molecular cloud complex. The young star at its center is less than 1 million years old. Its surrounding disk, called a protoplanetary disk, extends outward from the star for distances comparable to the width of our own solar system. Previous models of planet formation, built on decades of observation and computer simulation, described the process as gradual. Dust grains in the disk collide and stick together. Over millions of years, small clusters build into pebbles, pebbles into boulders, boulders into planetesimals, planetesimals into protoplanets. The final assembly of a rocky planet like Earth was estimated to require tens of millions of years, with significant variation depending on the disk's mass and the star's radiation environment. Webb's infrared imaging of protoplanetary disks revealed something that complicated that picture significantly. In multiple young disks, Webb detected structural features, gaps, and rings in the dust distribution that signal the presence of forming planets already clearing their orbital paths. Gaps in a protoplanetary disk indicate that a planet has grown massive enough to gravitationally sweep the material from its orbit, opening a clear lane in the dust. Finding those gaps in disks younger than 1 million years suggests that at least some planet formation proceeds on a dramatically faster timescale than the standard models predicted. Objects massive enough to clear orbital gaps, likely comparable to Neptune or larger in mass, can apparently assemble within the first million years of a disk's existence. 1 million years sounds long in human terms. In planetary science terms, it is extraordinarily fast. A confirmed study using Webb's data on a young disk in Taurus showed a gap structure consistent with a forming planet, roughly the mass of Saturn, already clearing its orbit in a disk estimated at less than 500,000 years old. That result, published and peer-reviewed, represents one of the youngest confirmed planet formation signatures ever recorded. The implication extends beyond any single system. If giant planets can assemble within the first 500,000 to 1 million years of a disk's existence, their gravitational influence on the disk begins far earlier than models assumed. Giant planets act as architects of the rest of the planetary system, their gravity scattering material, creating resonances, and shaping the final configuration of smaller rocky planets. An early forming giant changes the entire construction plan. This finding feeds into long-standing debates about why our own solar system's architecture looks the way it does, and whether systems with early forming giants produce rocky inner planets that are more or less likely to be habitable. Webb continues observing protoplanetary disks across multiple star-forming regions. Each new disk adds a data point to the formation timeline, and the picture emerging is one of a process more rapid, more violent, and more varied than the model described. But while Webb was rewriting the timeline of planetary birth, a completely different measurement problem was sharpening, one that goes beyond any single galaxy or system, one that involves the expansion rate of the entire universe. And Webb's contribution to that problem made an already tense disagreement significantly worse. The Hubble tension, two answers that should be one. The universe is expanding. Every large-scale structure in the cosmos is moving away from every other large-scale structure, carried apart by the stretching of space itself. This has been confirmed since Edwin Hubble measured it in 1929. The rate of that expansion is described by a number called the Hubble constant, and measuring it accurately is one of the most important goals in cosmology. The problem is that two different methods of measuring the Hubble constant give two different answers, and they disagree by enough to matter. Method 1 reads the early universe. Scientists analyze the cosmic microwave background, the faint radiation left over from roughly 380,000 years after the Big Bang, and use it to calculate the expansion rate predicted by the standard cosmological model. This method is precise. Its result? The universe is expanding at about 67 kilometers per second per megaparsec, a unit describing how fast space stretches per unit of distance. Method 2 measures the modern universe directly. Scientists use a chain of distance measurements, starting from nearby pulsating stars called Cepheid variables, whose brightness cycles reveal their true luminosity, extending outward to supernovae in distant galaxies that serve as reliable distance markers. This method gives a consistently higher number, around 73 kilometers per second per megaparsec. 67 versus 73. That gap sounds small. In cosmology, it represents a fundamental crisis. If both measurements are correct, then the early universe and the modern universe obey different expansion rates, which means something changed during cosmic history that the standard model does not account for. New physics. Possibly a new form of energy that altered the expansion rate at some point between the early and modern universe. If one measurement has a systematic error, then one of the world's most trusted measurement techniques is flawed in a way that has not been identified despite decades of checking. Webb was supposed to help resolve the tension by improving the precision of the Cepheid-based method. Hubble's measurements of Cepheid variables carried uncertainties from crowding, the fact that in distant galaxies, individual Cepheid stars blur together with neighboring stars in Hubble's images. Webb's sharper resolution was expected to disentangle those blended images and check whether the crowding was biasing the distance measurements. Webb checked, and the Cepheid distances did not significantly change. The higher expansion rate from the modern universe measurements held up. Webb confirmed that the local measurements were not being driven by the crowding error that some scientists had hoped to identify. The tension did not resolve. It sharpened, confirmed in 2003 in a published study using Webb's Cepheid data. This means the disagreement between the two methods is real and currently unexplained. The standard cosmological model cannot account for it. Something in the history of the universe, in its energy content, its expansion history, or its fundamental physics, does not match between what the early universe measurement predicts and what the modern universe measurement finds. Webb confirmed the problem is genuine. What caused it remains one of the most actively debated open questions in all of physics. And it connects directly to something even more fundamental that Webb's observations are reshaping: the nature of time itself at cosmic scales. Time itself runs differently across the universe. Time feels fixed. A second lasts a second. An hour lasts an hour. The clock on your wall and the clock in your phone agree because they exist in the same gravitational environment, moving at similar speeds through space. Time feels universal. At cosmic scales, confirmed physics says otherwise. Einstein's general theory of relativity, tested and confirmed by over a century of experiments, tells us that time runs at different rates, depending on two things: the strength of the gravitational field at a given location, and the speed of motion relative to an observer. Clocks in strong gravity tick slower than clocks in weak gravity. Clocks moving at high speed tick slower relative to stationary clocks. At human scales, these effects are tiny, but across the universe, they become significant. A galaxy far away from us is not just distant in space. It is moving away from us at a significant fraction of the speed of light, carried by the expansion of the universe. Time for objects in that galaxy, by the physics of special relativity, runs measurably differently relative to time as measured here. When astronomers observe a supernova explosion in a distant galaxy, the explosion appears to last longer to us than it would to an observer inside that galaxy. The rate of the explosion, its light curve, is time dilated by the galaxy's recession speed. This effect, called cosmological time dilation, is confirmed. It is directly observed in the light curves of distant supernovae. Supernovae in galaxies with higher redshifts, moving away faster, show stretched light curves in exact proportion to their redshift, just as relativity predicts. Webb's observations engage with this effect at deeper redshifts than any previous instrument. In 2023, a team used quasar variability data, covering archival observations as well as Webb contributions, to confirm cosmological time dilation at redshifts corresponding to the universe's first 2 billion years, earlier in the universe's history than the effect had been directly confirmed before. At those early epochs, the universe was expanding faster relative to its current rate, and the time dilation effect was stronger. Confirming the effect at that depth validates general relativity as accurate across a far larger stretch of cosmic history than prior data reached. But here is where Webb's contribution connects back to the tension from the previous chapter. The expansion rate discrepancy, the Hubble tension, means that the rate at which space was expanding at different points in cosmic history may not follow the smooth trajectory the standard model predicts. If the expansion rate changed in an unexpected way at some point in the middle of cosmic history, that change would alter the time dilation calculations for objects at those distances. Every timing measurement across those epochs would carry an uncertainty tied to the unresolved expansion rate problem. Webb is gathering data across exactly those epochs. Its observations of quasars, supernovae, and galaxies at intermediate and high redshifts are building a more detailed picture of the universe's expansion history. A picture that may eventually reveal whether the Hubble tension comes from something that changed the expansion at a specific period, or whether it points to something more fundamentally wrong with the Standard Model. The stakes of resolving that question extend beyond academic cosmology. The expansion history of the universe determines its ultimate fate. A universe expanding at the observed modern rate, driven by dark energy, will continue expanding forever, cooling and thinning into a frozen dark end state called the Big Freeze. Different expansion histories lead to different endings. What happens at the very end of the universe is one kind of cosmic frontier. Webb is also illuminating the opposite end, the very beginning, specifically one type of object from the earliest era that blazes with a violence that still defies explanation. Quasars that should not exist yet. At the center of certain early galaxies, something feeds. A supermassive black hole consuming gas and matter at such a ferocious rate that the energy released outshines every single star in its host galaxy combined. Some quasars outshine entire galaxies by factors of 1,000. They are the brightest, sustained light sources in the observable universe, and Webb has found them blazing in the early cosmos, at distances and ages that current models cannot fully account for. Quasars are confirmed objects. Their nature is well understood, accreting supermassive black holes, surrounded by superheated disks of infalling matter that radiate across the entire electromagnetic spectrum with extraordinary power. The physics of how they work is not in dispute. What Webb put in dispute is when they got there. Finding a quasar requires a supermassive black hole, already grown to a mass of hundreds of millions to billions of times that of a typical star. As established earlier in this journey, growing a black hole to that mass from a stellar remnant starting point requires close to 1 billion years at maximum, theoretically allowed feeding rates. The universe at 500 million years old had not yet had 1 billion years of time. Webb detected quasars at redshifts placing them in the universe's first 700 million years. Several confirmed detections, blazing, massive, actively feeding, already fully formed in their role as cosmic power sources, at an age when the formation models say the black holes driving them should still be growing. One quasar in particular, studied by a team using both Webb and ground-based telescope data, carries a black hole mass of roughly 1 billion stellar masses and exists at a confirmed distance, placing it in the universe's first 600 million years. The paper describing this object noted that producing a black hole of that mass in that time requires either starting from an unusually massive seed or feeding at rates significantly above the Eddington limit for extended periods. Neither scenario is comfortable within the Standard Model. Both require special conditions. Both are being investigated. The quasar detections do not stand alone. They sit alongside the early massive galaxies, the early supermassive black holes in quieter galaxies, and the over-mature stellar populations as part of a consistent pattern. The early universe produced extreme objects at a pace and scale that every instrument prior to Webb lacked the power to see clearly enough to measure. Webb made them measurable. And measured, they are collectively telling a story about the first billion years of cosmic history that differs from the Standard Model's predictions in ways that are too systematic and too consistent to dismiss as measurement error. Some cosmologists now speak openly about the possibility that the Standard Model is missing a chapter, an early chapter, one describing processes or conditions in the first moments or million years of the universe that accelerated structure formation beyond the model's predictions. Among the most discussed candidates for that missing chapter is a proposal that the universe did not just go through one period of rapid inflation, it may have gone through two. Did the universe inflate twice? Inflation is already the strangest event in the universe's history that science considers confirmed in its broad outline. In the first tiny fraction of a second after the Big Bang, the universe expanded by an almost incomprehensible factor, growing from a region smaller than an atomic nucleus to something the size of a grapefruit in less time than any human instrument can measure. This single burst of expansion smoothed out the universe, set up the tiny density fluctuations that became galaxies, and established the large-scale geometry that we observe today. Inflation happened once, in the Standard Model, the evidence supporting it is strong. The cosmic microwave background, smooth temperature pattern across the sky, the nearly flat geometry of the universe, and the scale-invariant spectrum of primordial density fluctuations all fit the predictions of inflation theory precisely. A growing number of theorists are now asking whether a second inflationary event, a smaller, briefer, later burst of accelerated expansion, might have occurred in the universe's first 100 million to billion years, and whether Webb's observations of the early universe could be explained by its effects. The idea is not new. It has existed in theoretical physics literature for years, under various names. What Webb did was give theorists a new dataset to match against their models. Early galaxies that are too massive, black holes that are too large, structure that is too developed. These anomalies, if real and systematic, need an explanation. A second period of accelerated expansion triggering a burst of enhanced density fluctuations that seeded faster, larger-scale structure formation offers one. The mechanism proposed in the most discussed versions of this idea involves a second brief domination of a scalar field, similar to the inflaton that drove the original inflation, that temporarily accelerated expansion before decaying and transferring its energy into matter and radiation. This energy injection would have created a new spectrum of density fluctuations on top of the primordial ones, effectively giving gravity additional seeds to work with at a later stage. If those additional seeds existed, the regions where density ran highest would have collapsed into structure significantly faster than the standard model predicts. The result would look exactly like what Webb found. Galaxies and black holes assembled earlier and at larger scales than expected. This remains a theoretical proposal, unconfirmed. No direct observational signature of a second inflation has been identified yet. But the proposal is testable. Specific versions of the second inflation idea predict specific signatures in the statistics of galaxy clustering at high redshifts, signatures that Webb's deep field surveys are beginning to have enough data to probe. Whether the statistics match the predictions of any specific second inflation model will become clearer as Webb accumulates more data over the next several years. The telescope's 20-year design lifetime means it has time to gather a dataset large enough to test these models rigorously. What is already confirmed is that the standard single inflation model, without modification, does not reproduce what Webb found in the early universe. Something additional is needed. Second inflation is one candidate. Enhanced dark matter clustering is another. Modified feedback physics is a third. All are on the table. All are being tested against Webb's expanding archive. And while the large-scale structure problem was generating debate about the universe's first moments, Webb was simultaneously discovering something about the chemistry of the early cosmos that had profound implications for an entirely different question. The chemistry of life spread earlier than anyone expected. Carbon is the backbone of life on Earth. Every living organism uses carbon as the scaffolding for its biological molecules. Proteins, DNA, lipids, the entire toolkit of biochemistry is built on carbon chains and carbon rings. This is confirmed and fundamental. For decades, the assumption in astrobiology was that complex carbon chemistry was a relatively late development in the universe's history. You need carbon, and carbon only forms inside stars. You need those stars to die and scatter the carbon through space. You need subsequent generations of stars and planetary systems to incorporate that carbon into rocky planets. The process, in the standard picture, takes billions of years. Complex carbon chemistry on the scale relevant to life was considered a late universe phenomenon. Webb found complex carbon molecules in galaxies over 10 billion light-years away. Polycyclic aromatic hydrocarbons, the same class of carbon ring molecules detected in the Southern Ring Nebula, were confirmed in the spectra of galaxies at high redshift, galaxies so distant that their light left them when the universe was less than 4 billion years old. The detection was made through Webb's mid-infrared spectrograph, which operates at wavelengths specifically sensitive to the vibrational signatures of these carbon structures. Confirmed. Published in 2023. Multiple galaxies, multiple independent spectroscopic signatures. The implications move in two directions at once. The first implication concerns the timeline of carbon chemistry in the universe. Complex carbon molecules forming in galaxies less than 4 billion years into cosmic history means that the molecular building blocks associated with organic chemistry were present and widespread far earlier than models assumed. The universe was seeding its galaxies with organic carbon chemistry during an era when many cosmologists had assumed the chemistry was still too primitive. The second implication concerns the universality of that chemistry. Detecting polycyclic aromatic hydrocarbons in multiple galaxies across a range of redshifts and galaxy types suggests these molecules are not rare or special. They form wherever conditions allow, which means across vast swaths of the early cosmos. The chemistry that underpins life on Earth may be standard issue across the universe, built into the galactic environment rather than being a lucky local accident. This does not confirm life elsewhere. It confirms chemistry elsewhere, earlier and more widely than the previous picture allowed. The gap between chemistry and life remains enormous. But chemistry is the prerequisite, and finding it early and widespread means the prerequisite was in place across more of the universe's history than anyone had calculated. Webb's mid-infrared instrument continues to survey galaxies across cosmic time for these carbon signatures. The dataset being built will eventually allow scientists to trace the rise of complex organic chemistry through cosmic history, from the first enriched galaxies to the modern era, constructing a chemical timeline of the universe that connects ancient galaxy evolution directly to the conditions that made planets like Earth possible. And that chemical timeline, it turned out, had an early chapter that was far more chaotic and violent than the modern universe suggests. Galaxy mergers happened, earlier and more often. The universe today looks relatively settled. Galaxies exist in loose groups and clusters, separated by vast voids. Interactions between galaxies happen, but major mergers, the collision and fusion of two large galaxies into one, are relatively rare events in the modern cosmos. Our own galaxy will collide with Andromeda in roughly 4 billion years, an event that counts as unusual in the current era. The early universe was chaos. Webb's observations of galaxy populations in the first few billion years of cosmic history confirm that the merger rate was dramatically higher than in the modern era. Galaxies in the early universe were closer together on average, the cosmos being smaller and denser. They moved through a thicker, more gas-rich environment. Interactions were frequent. Major mergers, events where two comparable mass galaxies slammed together and reorganize into a single larger system, occurred at rates that dwarf anything seen today. Confirmed studies using Webb data from the first 2 years of operations show galaxy merger rates in the first 3 billion years of cosmic history, running at roughly 10 times the modern rate. Multiple independent analyses, using different galaxy samples and different methods of identifying merging systems, converge on a similar excess over modern rates. This matters for the galaxy mass problem in a direct way. Mergers are one of the primary mechanisms through which galaxies grow. Two galaxies of moderate mass merging together produce a larger galaxy. If the early universe processed mergers 10 times faster than today, then galaxy masses accumulated faster than the standard model, built around modern merger rates extrapolated backward, would predict. The high early merger rate also drives bursts of star formation. When two gas-rich galaxies collide, their gas clouds slam into each other, triggering rapid compression and collapse. Star formation rates during major mergers can run tens to hundreds of times higher than in isolated galaxies. Early galaxies experiencing frequent mergers would have undergone repeated bursts of intense star formation, building stellar mass rapidly and enriching their chemistry quickly. This picture, emerging from Webb's confirmed merger rate measurements, offers at least a partial explanation for the overmassive, overmature early galaxies that started the chain of anomalies in Webb's first-year data. Fast mergers plus burst star formation could, in principle, produce galaxies that accumulate mass and chemical maturity on compressed timescales. Whether the early merger rate alone is sufficient to explain the full extent of the anomalies is still being worked out through simulations. Some models incorporating the higher merger rate narrow the gap with observations, but do not close it completely. Additional physics, whether in star formation efficiency, dark matter behavior, or inflation, appears necessary to fully reconcile the simulated early universe with the one Webb is observing. Webb is also confirming something specific about where those early merging systems concentrated. In the densest nodes of the early cosmic web, where multiple galaxy groups converged simultaneously. In those convergence zones, protoclusters were already assembling in the universe's first billion years, far earlier than previous observations could confirm. Those protoclusters are the seeds of the largest structures in the universe. And some of the structures Webb found inside them push the timeline problem to its most extreme expression yet. Structures so old, they challenge the universe's age. Inside Webb's deep field data sits a set of objects that have generated the most intense scientific debate of the telescope's early operational period. Several large-scale structures, groupings of galaxies connected by filaments of matter and organized across regions spanning hundreds of millions of light-years, appear in Webb's data at distances placing them in the universe's first 1 to 2 billion years. Galaxy clusters this large and this organized at this earlier date were not predicted by the standard cosmological model. Building a structure on that scale requires time. Gravity must first draw individual galaxies together into groups. Groups must merge into clusters. Clusters must connect into superclusters through filaments. Each step takes time, and the minimum time is set by the speed at which gravity can act across the relevant distances. At the scales Webb's deepest observations are probing, the standard model places the formation of large, organized structures significantly later in cosmic history. The early universe should contain the seeds of these structures, early protoclusters and dense filaments, but organized, large-scale networks of the type seen in the modern cosmic web should not be present this early. Webb found organized structure earlier. Several candidate proto-superclusters have been identified in Webb's data, some confirmed through spectroscopic redshift measurements of multiple member galaxies. The confirmations place these systems at distances corresponding to the universe's first 2 billion years, earlier than comparable structures in the modern universe, by a significant margin. This connects to a more radical proposal that has gained traction in the theoretical community since Webb began operating. Some researchers, examining the full set of Webb's early universe anomalies together, have proposed that the universe may be older than 13.8 billion years. The 13.8 billion year age is derived from the measured expansion rate of the universe and the standard cosmological model. If the expansion rate is different from what the standard model assumes, the derived age changes. The Hubble tension, the disagreement between early and late universe expansion rate measurements, already suggests the expansion history may not follow the standard model's smooth trajectory. If the universe expanded differently than the model predicts during some period, the calculated age could be off. A paper published in 2023 by researchers at the University of Ottawa and Jelenko University proposed that observations of early massive galaxies are consistent with a universe potentially twice as old as the standard calculation gives, around 206 billion years. If an alternative cosmological model involving interactions between light and dark matter is applied instead of the standard one, this proposal attracted significant media attention and significant scientific skepticism in roughly equal measure. The mainstream cosmological community has not adopted this view. The 26 billion year estimate relies on a non-standard model with significant theoretical challenges of its own. Most cosmologists consider it far more likely that the standard model requires adjustment rather than wholesale replacement. But the fact that such proposals are being taken seriously and published in peer-reviewed journals reflects the genuine depth of the challenge Webb's observations have posed to the standard picture. The universe is at minimum significantly more complex in its early history than the model predicted. Whether that complexity requires a different age, a different inflation model, a different dark matter model, or a combination of all three, is a question Webb's ongoing observations are actively shaping. And the cumulative effect of every discovery in this chain, from impossible galaxies to overmassive black holes, to complex early chemistry to large-scale structure appearing too soon, points toward a single overarching conclusion that cosmology is now being forced to confront. Every date in cosmic history may need recalculating. Cosmology runs on timelines. Every event in the history of the universe carries a date. The Big Bang at 0. The cosmic microwave background at 380,000 years. The cosmic dark ages ending around 100 to 400 million years. The peak of star formation at roughly 3 billion years. The formation of our solar system at 4.6 billion years. The appearance of life on Earth at roughly 3.8 billion years. Each date connects to the others through the physics of the standard cosmological model. Webb's observations have not invalidated any single confirmed date in that chain directly. The age of the universe, the timing of the cosmic microwave background, the age of our solar system, these remain consistent with their established values. Webb has not broken those anchors. What Webb has done is reveal that the processes filling in the timeline between those anchors moved faster and produced more extreme outcomes than the model predicted. And when processes move faster than the model says they should, the model's dates for when those processes began, peaked, and concluded need revision. Galaxy formation timelines need revision. The model placed the epoch of peak galaxy assembly at roughly 2 to 3 billion years after the Big Bang. Webb's early massive galaxies suggest significant galaxy assembly was already complete by 500 million years. The peak of assembly likely occurred earlier than the model described. Black hole growth timelines need revision. The model's picture of gradual supermassive black hole growth from stellar remnants across billions of years does not produce the objects Webb finds in the early universe. Either growth began earlier, proceeded faster, or started from more massive seeds than the model assumed. Any of those changes shifts the implied timeline of black hole formation backward. The reionization timeline has already been revised by Webb's data, with the clearing of the cosmic hydrogen fog confirmed to be more patchy and more driven by small, faint galaxies than prior models assumed. The detailed timing of when reionization completed in different regions of the universe is being actively rewritten as Webb's data accumulates. The timeline of organic chemistry in the universe has been pushed earlier by the detection of complex carbon molecules in galaxies over 10 billion light-years away. The implied onset of conditions relevant to life's prerequisites now extends deeper into cosmic history. Each revision individually carries weight. Together, they point toward a picture of the universe's first few billion years as a period of extraordinary productivity that the standard model underestimated systematically. The word systematically is important. Random errors scatter in all directions. Systematic discrepancies point in one direction consistently. Every Webb anomaly points toward faster, earlier, larger. That consistency is the hallmark of a model that is missing something real, rather than a collection of measurement errors. The scientific community is working through this methodically. Simulations are being rerun with adjusted parameters. Alternative models are being tested. New theoretical frameworks are being constructed and compared against Webb's growing archive. The process is active, ongoing, and generating significant output in the form of published research. What is already clear is that the timeline of the universe as written before Webb is a first draft. Webb is providing the material for the revision, and the revised timeline will describe a universe more productive, more violent, and more chemically rich in its youth than the version that cosmology operated on for decades. The telescope, with 20 or more years of operational life ahead of it, has used only the first fraction of that time. What it has already delivered to science is substantial. What remains ahead of it may be even more transformative. Webb has 20 years. We've seen 1%. James Webb was built to last. Its design specification calls for a minimum operational lifetime of 10 years. The actual fuel remaining for its orbital maintenance maneuvers, a more limiting constraint than the hardware itself, is sufficient to operate it for at least 20 years and possibly significantly longer. The precision of the launch trajectory that placed it at Lagrange Point 2 used far less fuel than the worst-case planning scenario required, preserving the reserve. 20 years. And the scientific community estimates that the discoveries described in this journey represent somewhere around 1% of what Webb will eventually produce. That estimate reflects the breadth of the telescope's mission and the scale of what remains unobserved. Webb is not a single-purpose instrument. It serves multiple scientific communities simultaneously. Cosmologists studying the early universe compete for observing time, with planetary scientists studying solar system objects, stellar astronomers studying star formation, exoplanet researchers studying planetary atmospheres, and galaxy evolution teams studying intermediate redshift populations. The scheduler allocates time across all of these programs in each observing cycle. Every observing cycle produces new data. Each new dataset is archived, made publicly available to the global scientific community after a proprietary period, and analyzed by hundreds of independent research groups. Webb's scientific output is not limited by the telescope's capability. It is limited by the number of scientists capable of analyzing the data it generates, and that number grows as more researchers train on the new wavelengths and new datasets Webb produces. The most anticipated future results cluster around a few key areas. The biosignature search for rocky planets around red dwarf stars requires decades of patient observation to accumulate enough transit data for confident atmospheric characterization. Webb's 20-year operational window is long enough to make genuine progress on this target, the one with perhaps the highest stakes of any scientific question humanity has ever asked. The earliest galaxy population, the objects existing in the universe's first 200 million years, remains sparsely sampled. Webb's confirmed early galaxy catalogue contains dozens of objects at the most extreme distances. Thousands more exist within Webb's detection capability, waiting for the observation time to be scheduled. A more complete sample will tell a much clearer story about how structure formed in the cosmic dawn, and whether the standard model can be patched or requires fundamental revision. The Hubble tension remains unresolved. Webb's contribution to the Cepheid distance measurement confirmed the tension is real. Future Webb observations of other distance indicators, including a class of pulsating stars called mirror variables, and a method using surface brightness fluctuations in galaxies, will add independent measurements to the expansion rate debate. If those methods converge on the same higher value, the case for new physics becomes significantly stronger. Dark matter's behavior in early galaxies is an open investigation. More kinematic data from early high-redshift galaxies, the kind Webb continues to gather with each cycle, will either confirm the discrepancy with cold dark matter predictions or show it fading at higher sample sizes. The universe placed a telescope 1 million miles away and waited. Webb opened its golden mirror and immediately found that the story of time was more complex, more surprising, and more layered than the version written before it launched. And the question it leaves hanging, the one that every chapter of this journey has been building toward, is the one that the most honest cosmologists will admit they do not yet know how to answer. What else about reality is waiting to be rewritten? Webb pointed at the edge of time and found that the edge was closer than we thought, that the objects near it were larger than they should be, and that the story connecting that edge to right now contains chapters we had not written yet. Every discovery in this journey was an answer, and every answer opened a question that did not exist before the answer arrived. That is the pattern science follows. It is also the pattern that suggests we are nowhere near the end of revision. The galaxies that should not have existed at 300 million years after the Big Bang are confirmed. The explanation for how they formed is not every proposed mechanism: accelerated star formation, enhanced dark matter clustering, stronger primordial density fluctuations, a second inflationary episode. Each one is a hypothesis waiting for a confirming dataset. Webb is gathering that dataset right now. The supermassive black holes that appeared too early are confirmed. How they grew so massive so fast is not confirmed. Direct collapse black holes remain theoretical. Super Eddington feeding remains unobserved in the early universe at confirmed scales. The black hole first galaxy formation scenario is supported by data, but unconfirmed as a primary pathway. The Hubble tension is confirmed real by Webb's Cepheid data. Its cause is not confirmed. New physics between the early and modern universe is the most widely accepted category of explanation. What that new physics specifically is remains completely open. The complex organic carbon molecules in early galaxies are confirmed. What they imply for the timeline of life's prerequisites across the universe is a question that no current instrument can answer fully, and that Webb itself can only partially address. These open questions are not failures of science. They are the leading edge of it. Every generation of scientists inherits a model that explains the evidence available to them. Every new instrument that pushes observational capability beyond the prior generation's limits finds the model's edges, the places where it runs out of explanation. Webb found a remarkable number of those edges quickly. What comes after the edges is the territory future science will map. Some of it will be mapped by Webb itself, as its ongoing observations accumulate into datasets large enough to test the competing models more rigorously. Some will require the next generation of instruments, including the Nancy Grace Roman Space Telescope and the extremely large telescope currently being built in Chile, both of which will use Webb's discoveries as their starting points. And some of what comes after the edges may require ideas that have not been written yet, physics that has not been formalized, models that have not been proposed. The history of cosmology is full of moments where the answer to a stubborn anomaly turned out to be a concept no one had considered before the data forced them to. Dark energy was not predicted before the supernova observations that revealed the accelerating expansion. Dark matter was not seriously proposed before galaxy rotation curves made the missing mass impossible to ignore. Inflation was not invented until the flatness and horizon problems of the original Big Bang model demanded something dramatic to solve them. Webb's anomalies are demanding something. The demand is clear even if the answer is not. Somewhere in the data this telescope is collecting, possibly in the spectra of an ancient galaxy that has not yet been scheduled for observation, possibly in the rotation curve of an early disk galaxy that has not yet been fully analyzed, possibly in the atmospheric transmission spectrum of a rocky planet that has not yet received enough transit observations. The next revision of reality is waiting. That revision will not come from a single dramatic moment. It will come the way all scientific revisions come, slowly, then suddenly, accumulating in data archives and preprint servers and conference presentations until the weight of evidence tips the balance and the model changes. Webb is building that weight, one infrared photon at a time.